Welcome back, everyone. This morning it's our pleasure to welcome Cornelia Drutu from Oxford, who will speak to us on property T and a-T-menability for Banach spaces.
It's on. It works. All right. So first I'd like to thank the organizers for inviting me to give a talk at this wonderful conference. I thought of my talk as a colloquium talk, so I will define a number of things. I might not have chosen the right things to define, so if you need anything else to be defined among the concepts that I'm using, please don't hesitate to ask. And of course, for the experts in the room, I apologize for going rather slowly on things that may look obvious to them. Let me put things into a general setting. So why should we be interested in these two properties and moreover for Banach spaces? Because, let's say, a generic method used in many areas, geometry, algebra, and combinatorics, is to understand a certain object by drawing it accurately on the right kind of board. This is something that mainly was used in theoretical computer science and combinatorial optimization. The way they proceed to solve a certain problem is that you try and draw your structure faithfully enough on a good enough board. What does that mean? First of all, you formalize your problem into a combinatorial structure, and then you try to understand it by embedding it into a metric space that you understand, and then you use that ambient geometry that you understand to design an algorithm and solve your problem. And we sort of stole this technique from them. And in our setting, geometric group theory setting, of course, the first question is, what kind of objects would we try to understand? So what are the objects that we are drawing? What is a faithful enough portrait from our point of view? And what is a good enough board for us? Now, of course, all these questions are debatable. But let me say what I mean by each of them. So first of all, what will be the objects that I will be trying to draw faithfully? Throughout the talk, there will be groups. In the most general form, they will be topological groups, compactly generated, but non-compact. But in fact, most of the time, they will be finitely generated groups that are infinite. So finite groups are not interesting for me in this setting. And then what is a faithful enough portrait? If we just look metrically speaking, so from a metric viewpoint, and again, we just look at our objects, but of course this makes sense for a general metric space. If we consider our group endowed with a left invariant metric, for instance, if the group is finitely generated, we just endow it with a word metric, and we want to sort of draw its portrait in a space, that means we would like to have a map from our group to that metric space, satisfying this kind of inequality. So if we look at the distance between the images and we try to compare it to the distances in the beginning, the only thing we want to is that this distance, this new distance, increases to infinity as this increases to infinity, but the speed is not an issue. So we just want to have an inequality like that, and that we have on the left-hand side and the right-hand side two proper functions, well, obviously defined on R plus and taking values in R plus, and going to infinity as the variable increases. But I should say that if the metric that we consider is a length metric, so that it is given by the shortest path joining 2 points, and in a certain sense it is the case for word metrics in finitely generated groups, then this inequality is automatically a linear inequality. So we can always assume that this function here is linear. So it's L times, so it's a Lipschitz inequality, the first one. And the only other one that's more mysterious is this one. But anyway, this is a good enough uniform embedding, metric embedding for us. But if we want more, so if we want not to lose the group structure, we would like to have this map to be equivariant. So that means equivalently, in fact, we want the group to act on the metric space as well, and we want that every orbit map is a uniform embedding. I mean, of course, the lower bound will differ a little bit. It will depend a little bit on the group, but we want it to be uniform. So that is, we want to be able to copy inside the group inside the metric space, the group acting on the space, and this action restricting to the orbit, and we want the orbit not to be crumpled inside the space, so to sit sort of well enough, but distorted. We don't mind about that. And then an equivalent way of stating exactly the same thing is we want the group to act on the metric space, and we want the action to be proper in the usual sense. If you look at a bounded set and this translates, the number of translates that intersect the initial bounded set should be finite, and the number of elements doing it should be finite as well. And then the last question, so these are the objects. This is a faithful enough portrait for me. And then what is the right board? So as mentioned before, a finitely generated group, for instance, has a uniform graph attached to it, the so-called Cayley graph, which I'm not defining because I'm sort of assuming that everybody knows that. So if you want it to be defined, speak now. You have a few seconds. No, nobody wants it? Okay, that's fine. So we can always identify a finitely generated group with a set of vertices of a uniform graph, the Cayley graph. But of course, if the group is infinite, the graph is infinite. And I mean, if we look at what happens to finite graphs, each of them can be embedded. I mean, if we're lucky, we can represent it on the usual board so that these are planar graphs well enough. But if not, we have to increase the distance as the graph becomes more and more complicated. So you'd say that for an infinite graph, an infinite dimensional board would be enough. In other words, a Hilbert space. So that is a good enough board, of course, but and the group having this representation, so having an uniform equivariant embedding in the previous sense, is called a-T-menable, or equivalently, we say that such a group has the Hagerup property. It's an important property. Many groups satisfy it, but many groups don't, as we shall see. So let's see what this would give us. So first of all, what would be the groups that have such a nice representation on an infinite dimensional board? And equivalently, of course, let me remind you, either we ask for uniform equivariant embedding, or we ask that the group has an action by metric isometries on a Hilbert, so nothing linear here, just metric isometries, and we want this action to be proper. And groups that satisfy this are amenable groups. So this explains part of the terminology. So these are the groups, really the amenable groups introduced by John von Neumann when he wanted to explain why the Banach-Tarski paradox is satisfied from dimension 3 on and not in dimension 1 and 2. And the reason was that in dimension 1 and 2, the group of isometries are amenable, and in higher dimension, they're not. So it's exactly that one. And they're all a-T-menable, so they're all good to represent. Other set of examples, all the groups that have a proper action on a real or a complex hyperbolic space, or equivalently, all the fundamental groups of manifolds that can be covered by real or complex hyperbolic spaces, in particular free groups, so that's very far from amenable, in fact, quite the opposite, but they are a-T-menable, so they are representable in Hilbert spaces. And the last class, and I will explain later what I mean by this. So there are various models of random groups, and this time we're really talking about finitely generated and in fact finitely presented groups. And if we adjust our model such that we only look at groups that have few relation by comparison to the number of generators, then the generic group is a-T-menable. So that's a good advertisement that really a-T-menable is a great property because in a certain sense, in a certain model, the generic groups are a-T-menable. And well, just to show you that if we do have such a representation, then it's great news. It's a result by Hickson and Kasparov that a-T-amenable groups satisfy the Baum-Kohn conjecture. So the same trick from combinatorics and optimization works here as well. If the groups are representable well on a nice enough board, then we can say things about them. Now, unfortunately, this covers many interesting groups, but not all of them. And in fact, many interesting groups satisfy a strong opposite. But before saying that, let me clarify a little bit things about isometries of Hilbert spaces, metric isometries of Hilbert spaces. So just more to fix the notation, because I imagine these are well-known facts. And then I should also say that later on, so I mean, the a-T-menability property, the classical one, is the one considering a Hilbert space as a good board. But in fact, as you're already guessing from the title, later on I will consider as good boards also LP spaces and in more general Banach spaces with good properties. And in that case as well, it will be exactly the same definition. I will look at groups that have proper actions on such Banach spaces by metric isometries. So let's then look at the structure of metric isometries on a general Banach space. Now this one is an old result of Mason and Ulam, and it says that what we know in Rn is also known for Banach spaces. So in Rn with the standard metric structure, the isometries always have the same form. They have a solid rotation and then a translation. And the same thing actually happens for Banach spaces. All the metric isometries, but I'm talking only about the real Banach spaces. And now it's the time to say that for me, in this talk, all the Banach spaces are going to be real. I'm not going to look at the complex Banach space, because otherwise it's a little bit more complicated. But I mean, for all the things that I'll mention, this is not an important restriction. So all the isometries, the metric isometries of real Banach spaces are fine. So that means they look exactly as for Rn. We have a unitary operator, so a linear part, and then a translation part. Which means that if I want to look at a group acting on a Banach space by metric isometries, then I want, first of all, to have a representation of the group. So this is going to give us the linear part for all the elements. So a unitary representation, obviously. And then I want a translation part for each element. So that means I want to associate to every element of the group a vector. And then I want all this to give me an action. So that means when I define the action in this way, the unitary part given by this one, and then the translation part by this one, I want the equations of the representation to be satisfied. And if we rewrite them, these are going to give us exactly that this map has to satisfy the equations of a cocycle. But I mean, that's just terminology. Whatever you need to know is already there. So these are the kind of actions that we're looking at. And moreover, if the group has a topology, we have the extra condition that the action is continuous, which means that the orbit map should be continuous. So these are the actions that we look at. And now, as I said before, even for actions on Hilbert spaces, there are plenty of groups that don't satisfy the a-T-menability property. In fact, they satisfy a very strong negation of that one, which is the property TIFR. So in a way, the structure is incompatible with the Hilbert geometry. So the property TIFR is precisely requiring that when we make the group act by metric isometries on a Hilbert space, we always have a global fixed point. Equivalently, we have that every orbit is bounded, but since the Hilbert spaces are uniformly convex, whenever you have a bounded orbit, you just look at the smallest ball containing that bounded orbit, and the center is fixed. So bounded orbit is equivalent to fixed points. And so what kind of groups satisfy this strong opposite? Well, to begin with, there is an interesting split in the group of isometries of symmetric spaces of rank 1. So if we look at the groups of isometries of the hyperbolic spaces over the quaternions and the hyperbolic plane over the octonions, these groups, which are Lie groups, have the property T, and all their lattices have the property T. So they are very incompatible with the Hilbert geometry. The group of matrices with integer coefficients, as soon as n is at least 3, has property T. And more generally, lattices in simple groups of rank at least 2, and even more generally, lattices in semi-simple groups such that all the factors have rank at least 2, they have property T. And again, if we consider a random group structure, a random group model, but this time one in which the relations are comparatively numerous with respect to the number of generators, then the generic group will have property T. So this again shows that this is a property that we want to study. And well, as it turns out, I mean, it's bad news in a way. It's bad news, for instance, for trying to apply the Hickson-Kasparov result, but it's also a very interesting property, and it's relevant in many settings. For instance, in combinatorics, it provided the first hands-on construction of expander graphs with any number of vertices. In algebra, because it implies structural properties of the infinite groups that enjoy these properties. So for instance, finite abelianization, they do not split as amalgamated products or H&N extensions. In ergodic theory, it implies rigidity results. And in fact, in many ways, you can see the property T as a rigidity result. And in fact, this way of defining it is not the initial one. The initial one was to say that the trivial representation is isolated in the Feld topology. So in many settings, and in many ways, you can look at this property as a rigidity result. And in operator algebras, because it's connected in more than one way to the Baum-Cohn conjectures, actually, the various versions of the Baum-Cohn conjecture. And, well, so these are classical properties related to our attempt to represent groups in Hilbert spaces. And now we can tweak it in various ways. And the first way to tweak it is we just replace Hilbert spaces by Banach spaces. And well, before I actually mention a few versions, let me say a few things. So yes, so there are two ways, in fact. I will only mention two ways of modifying these two properties. So one will be, I will just replace Hilbert by Banach. The other one, I will look at that affine action, but I will modify it a little bit. So the class of affine actions will be slightly enlarged. And before I mention this, and most of the times when modifying these two properties, the property T will become stronger and the a-T-menability will become weaker. And a general remark that actually people believed even sort of as soon as the first strengthenings of property T appeared was that when one strengthens property T and therefore sort of weakens the a-T-menability, the lattices in rank 1, all of them, will fail to have the strong versions of property T. So we're speaking here of lattices over the quaternions or lattices in the lattices of isometries of the octonian plane. Eventually, they will even become a-T-menable in that weaker sense, while higher rank lattices will tend to preserve even the stronger version of property T. And as you will see, actually, this sort of general feeling that people had, which is that the property T of rank 1, groups of isometries of rank 1 symmetric spaces, and more generally hyperbolic groups, is not as robust, is confirmed. In all the cases that I'll mention, it's in fact confirmed, or conjecturally confirmed, in fact. Yeah, it's true. I mean, there is a conjecture in that direction, and it makes sense. Right, so let's first look at the sort of easiest generalizations of property T and a-T-menability. it just replaces Hilbert spaces by LP spaces. And even in this case, the picture becomes quite complicated. So the idea would be I'm just fixing P between 1 and the infinity. In fact, in many cases, what I'm saying will also be true just for every P positive. It's just between 0 and 1 there are various complications. But via modifications, in fact, pretty much most of the things I'm saying will be true there. And then the version of property T that is, appears in this case would be we're just asking for that fixed P that the group has the property that every action by metric isometries on an LP space has a global fixed point. So that's property T. And at the opposite, we ask that the group has one proper continuous action by affine isometries on an LP space, and we'll call this a FLP meanable. And, well, I mean, the importance of this property is, as it turns out, in fact, I'm anticipating here a little bit. As it turns out, for P large enough, this property is stronger than property T, and therefore a number of rigidity results will hold under weaker assumptions. For instance, this is a result of Andres Navas. And the importance of the opposite property is that, as Kasparov and you announced, it also implies Novikov. So let's compare these two sets of properties with the classical ones. And actually, between 1 and 2, FLP is equivalent to T. So, in fact, for P strictly larger than 1, this is due to a result of Delorme-Guichardet. And for P equal to 1, it's a result of Badar-Gelander and Monod. Now, the thing here is that what Delorme and Guichardet proved is that property T is equivalent to the fact that every action by affine isometries on an LP space has bounded orbits. And for P larger than 1, LP spaces are uniformly convex, and therefore bounded orbits is equivalent to fixed points. For P equal to 1, L1 is not uniformly convex, and a priori you'd say that the fixed point property is weaker. So in order to show that it is exactly the same, one has to show, there is something else to do. So there is a strategy, and that was done by Badar-Gelander and Monod. In any case, for any P, FLP implies T. And for P large enough, it is proved that it is strictly stronger. So it's really stronger than the property T. So the first example was actually, it's sort of implicitly proved in the work of Pansu, and it was basically explicitly extracted from there by Cornelia, Salle, and Valette. So they showed that the group of isometries of the quaternionic hyperbolic space, so it has property T, but it starts acting properly on LP spaces as soon as we go beyond this number, which is the conformal dimension of the boundary of the quaternionic hyperbolic space. This is true, of course, for the full group of isometries, and it is also true for the lattices. And this was generalized by Yu and Bourdon. Actually, Yu and Bourdon both proved that all the hyperbolic groups act properly on an LP space for P large enough. And it is Bourdon that actually noticed that it just suffices to go beyond the conformal dimension of the boundary of the hyperbolic group. So hyperbolic groups have a boundary, and there is a notion of dimension. The most natural one is this one, the conformal dimension. And if you go beyond that, the group starts acting properly on an LP space. And since there are plenty of groups with property T, as for instance, those lattices mentioned here, and also the random group model will show there are plenty of them. So they will have property T, but they will fail to have FLP for P large enough. In fact, they will become a FLP meanable. On the other hand, if P is close to 2, in fact, for P between 2 and 10, the relation is not known for the moment. So there are no examples. there is one thing that is known, which is that for every group with property T, one can go a little bit beyond 2. But this quantity a priori depends on the group. So this is an argument of David Fisher and Margulis. And as announced before, if we look at higher rank lattices, like for instance SL and Z for an at least 3, these have all the range of fixed point properties. So all the actions by isometries on an LP space always have a fixed point. And that was proved by Bader-Furman, Gelander, and Monod. So this is the sort of setting. So between 1 and 2, nothing new. It's equivalent to T or AT respectively. For P larger than 2 and definitely large enough, FLP becomes stronger and AFLP becomes considerably weaker. Now, another way of tweaking these two properties is by tweaking the affine action. So before, the affine action had a unitary part and a translation part. And now we just allow for actions where the linear part is not going to be a unitary representation, but a uniformly bounded representation. And that will make the affine action uniformly by Lipschitz with the same constant. And this is why we call them affine uniformly by Lipschitz actions. And okay, so first of all, I mean, the generalization is obvious. We're going to consider, instead of affine isometric actions, affine uniformly by Lipschitz actions. And it's the same thing. We're just going to either ask that every such action has a bounded orbit, that's the equivalent of property T, or we're going to ask that there exists such an action that has that is proper. And well, unsurprisingly, higher rank lattices have the fixed point property even in this case, and even for LP spaces, if P is larger than 1. So if we make a higher rank lattice act on an LP space or on a Hilbert space with this weaker kind of action, we still have even a fixed point, in fact. While in rank 1 and for hyperbolic groups, this is conjectural. So it's a conjecture of Shalom that every hyperbolic group, again, including all those with property T, will have a proper action on a Hilbert space by this kind of actions. So not isometric, but affine uniformly Lipschitz. There is even a weaker version of that, which is we're just asking that every hyperbolic group acts on a Hilbert space with affine uniformly Lipschitz transformations, by affine uniformly Lipschitz transformations with unbounded orbits. And the situation up to now is that only one case is known. The lattices of isometries of the quaternionic hyperbolic space, these are proved to satisfy the strong conjecture. So Nishikawa proved that they act properly on a Hilbert space by affine uniformly Lipschitz actions, and the rest is not known. Right. So, of course, you can ask questions at any point. Right. And I was mentioning from the beginning that a source of examples are the random groups in various models. And I will only explain one of them. There are two that are more popular. And in order to explain that one, let me begin by a few remarks. First of all, if you look at all the finitely generated groups, this is a class of power continuum. Even if we look at two generated groups, it has power continuum. So that means that any probabilistic model is complicated to design because we would be working with this kind of set. While if we work with finitely presented groups, this is a countable set. So that's a reasonable setting for all the random groups models. So we are only going to look at finitely presented groups. There are, of course, random group models in this setting as well, introduced by Gromov, but there are few results known in that case. So that's what we were looking at, only finitely presented groups. Then another thing is that, pretty obvious, that if a group has a finite presentation, then it has a presentation in which all the relators have length 3. So provided that we add enough generators, we will always make sure that all the relators have length 3. So essentially, in our model, we are going to look at groups with a finite presentation in which all the relators have length 3. And the model that both models that are sort of where results are known depend also on the choice of a certain parameter called the density. So we choose such a parameter between 0 and 1. And depending on the choice, we will have a different model. And the model that I consider is the so-called triangular density model. And its advantage is that it is closely connected to a known model of random graphs, the Erdős-Renyi model. And in fact, many of the results, and one of the central results that I will mention comes precisely from that random graphs model. And the model is this one. So we fix an M, and we look at all the finitely presented groups that have M generators, and then have relators of length 3, and these are going to compose a set of this cardinality. So we look at all the relators of length 3, so they are the cardinalities of order M cube, and then we take power D of them. So this density is actually measuring how many relators we take, and depending on D, whether D is large or small, that will mean that we take comparatively few relators or many relators. And we just pick at random a set of relators of this cardinality. And this is going to be my model. And we take all the groups defined by such presentations. Now, of course, there is a small objection here, is that several, in fact, quite a few, but that's what, this is all that we can do. First of all, we don't seem to be working with groups. We seem to be working with presentations, but this is not a problem because one can easily show that the groups that are isomorphic compose relatively small parts. So essentially, we are working with groups. And then we say that a certain property holds asymptotically almost surely if, so we increase M, so that means we increase the number of generators. So essentially we increase the number of finitely presented groups. And as M goes to infinity, we want that property to be satisfied with a probability that increases to 1. And so this is the model of random groups. And this is the kind of properties, generic properties that we consider. And let's see what are the things that are known. Well, first of all, if we take too many relators, so if the density is larger than a half, then Gromov proved that the group is essentially trivial. So it's either trivial or Z2. So that means we'd better restrict to densities less than a half. And in that case, the change is radical. The generic group is infinite hyperbolic. So this is again Gromov. Now, if the density is larger than a third, then the group has Kazhdan property T asymptotically almost surely again. So this was proved by Zhuk, and more recently, his proof was refined and improved and in fact generalized to other models by two brothers, Kotovsky. So that means that if we take our density between a third and a half, the generic group is infinite hyperbolic and with property T. So that means it will be one of those groups that have property T, but not a very robust one. So they will start acting also properly on LP spaces. And actually this, as I said, follows actually from a result from random graphs. So it follows from the fact that random graphs are expanders in the Erdős-Renyi model. That was a result from the 80s by Friedman. While if we go below the threshold, a third, in this model, the group is in fact free, and in particular a-T-menable. This is due to Antoniuk, Luchak, and Shatkovsky. And there are some interesting phenomena at the threshold. So for instance, if d is equal to a third, but I won't mention that. So this is the situation. And so since we are looking at random groups, and essentially we're going to look at random groups in a model where the density is between 1/3 and a half, that means we're going to look at groups that are hyperbolic, but with property T. We would better analyze them via a set like this. So for a given group, I'm just going to measure all the fixed point properties that it enjoys. And so I'll just look at all the P's such that the group has the fixed point property for the corresponding LP spaces. And well, by what I said before, either this set is empty, or if it contains any P, it must contain this interval 1, 2. So that means if we want it to be non-empty, we have to consider groups with property T. And it's in a way a measure of the strength, the robustness of the property T for that group. Knowing again that, for instance, for lattices, it's not interesting because for lattices, it's the entire interval. So that's not the kind of groups we want to consider. Hyperbolic groups is, though. And we know two other things about this set. The first one is that it is open. So it's open in this interval, or as I said before, if we tweak a little bit the definition and we go in the interval 0, infinity, then it is generally an open subset of R. And moreover, it is an interval, actually. This is a result of Mikael de la Salle and Maragchi. So it looks like this, which means that now we have this interval, and in particular, this parameter here that is measuring the strength of the property T for a certain kind of group. And again, as I mentioned before, if we want this to be interesting, so that means if we want this set, this interval to be non-empty but not the entire thing, well, the only set of examples that we have would be hyperbolic groups with property T. So these are the kind of groups that we're going to analyze via this set. And in the setting of random groups, here is what we get. So there was an initial result of, with John Mackay, and that was later improved by Tim Delat and Mikael de la Salle. If we have a fixed density, in the triangular density model, well, the generic group is infinite hyperbolic. That's actually not our result, it's Gromov's, as I said before. And this upper bound of the interval of fixed point properties is comparable to the conformal dimension of the boundary in this sense. And the conformal dimension of the boundary is at most a constant times the logarithm. So we have these two sets of inequalities. So this is what we had proved initially. So F increases with the conformal dimension of the boundary, and it increases with the number of generators in this way. There was a result before ours about random groups, but the bound only obtaining a lower bound, and this lower bound actually converged to as m went to the infinity. But there is the good news is that there is an improvement now due to Isar Oppenheim. So he actually proved that this lower bound is linear. So he removed the square root, which means now that what we know for the density between a third and a half is that this f of g measuring the strength of the fixed point property is comparable, grows at the same rate as the conformal dimension of the boundary, and they both grow at the rate of logarithm of n.
What's the dependence of C1? It depends only on the density.
So there is a bi-Lipschitz bit, but there is also a C1 bit. Yeah, depends on the density. Yes. Right. Well, so before proceeding, well, we should also look at the other extreme, so the proper actions on LP spaces, and say the strength of that property. And this one can be measured, of course, by looking at all the parameters such that G acts properly on LP spaces. And for such a set, less is known. So for instance, it is not known if it is open or closed, but by the same theorem, I mean, as a consequence of the same theorem of de la Salle and Maragchi, it is known that it is an interval. But so it's either open or closed. The important bit is that here too there is another interesting parameter appearing, so the infimum of this interval, measuring sort of the strength of the a-T-menability of such a group. And by the result mentioned before of Yu and Bourdon, for group hyperbolic groups, we do know that this parameter is at most the conformal dimension of the boundary. So now we have two parameters, one measuring the strength of the fixed point property and the other one measuring the strength of the a-T-menability. And again, we have to restrict to the cases where we know that both are non-empty. In this case, it's just the hyperbolic groups with property T up to now with the results that we have. And there are some natural questions. Well, obviously, we have this inequality. Do we have equality? The second one, can we really relate, as that theorem about random groups seems to point out, can we connect any of these two with a geometric feature of the group? And in particular, for the hyperbolic groups with property T, can we relate either of them to the conformal dimension of the boundary, either by a formula or by a double inequality? And now for the fixed point property, unfortunately, or fortunately, I don't know, the answer is negative. So one can produce groups that stop having the fixed point property at 10, while the conformal dimension of the boundary and the parameter measuring the strength of a-T-menability can be made as large as possible. So that shows two things, that the gap between f of g and p of g can be made as large as we want. And the second one is that at least the fixed point property cannot be related for all the hyperbolic groups with at least this geometric feature of the group. And the technique to prove it is that, well, it's a technique coming from small cancellation. So it's a technique that was introduced by Olshansky, again related to the work of von Neumann and the von Neumann-Day conjecture. Because we can do the following construction. Given a finitely presented group, in fact, any finitely presented group, and given a hyperbolic subgroup, we can produce a hyperbolic group that has P as a quotient and H as a subgroup. So in particular, if we take as a finitely presented group, let's say, a lattice of isometries of the quaternionic hyperbolic plane, now that one starts acting properly on LP spaces from P at least 10. And then we just take a hyperbolic group with any range of fixed point properties. By the random group theory, we know that we have hyperbolic groups that have more and more fixed point properties, and we just embed it into our group. And then we'll just have a group that can't have the fixed point property after 10 because this property is inherited by all the quotients. So it has to stop at 10, but it can't start acting properly before n, because H will have the fixed point property before n. So it's if H is infinite, and therefore we will have big stabilizers of a point, so we can't have a proper action. I should also mention here that the same construction allows to construct plenty of hyperbolic groups that are neither a-T-menable nor with property T. In case you are wondering, there's no dichotomy in the class of hyperbolic groups. There are groups like that. Now, that being said, this construction, as I said, is with small cancellation. And small cancellation, and at least in particular this construction, is anything but natural. It's a sort of like you tweak the thing until it does what you want to. So it's not a generic construction, combined with the fact that generically this is not what happens. So for random groups, on the contrary, we know that f of g is comparable with the conformal dimension of the boundary, and it is comparable with p of g. One would say that most of the hyperbolic groups will have f of g comparable to p of g and the conformal dimension of the boundary. And the question is what condition to put under which we do have such an inequality. Because, as I said, generic hyperbolic groups do have it. And this is not a generic construction. It's a very distorted construction. And then, of course, there is also the question still open, is that parameter measuring the properness, the a-T-menability, is that one comparable to the conformal dimension of the boundary? Again, as a general theorem, not asymptotically or more surely, not in the setting of random groups. Now, so this is just by looking at actions on LP spaces. And it's already, this is what we get. But then we can look at actions on any kind of Banach spaces and look at the fixed point properties in that setting. So we could, for instance, be sort of greedy and say, well, I would really like to define a spectrum of fixed point properties that is really covering everything. Because the previous spectrum, the one in that set, was only restricting to LP spaces. So, well, we could say, I'm just taking all the Banach spaces for which G has a bounded orbit property. The only problem for that one is that it is not a set, because the class of Banach spaces is not a set. But if we restrict to countable groups, in that case, it suffices to restrict to separable Banach spaces, and that is a set. So we could look at that set. And that set will really cover all the fixed point properties that a group has. There is a topology of that set. And this was defined by Mikael de la Salle. And for reasons related to that topology, if we look at all the Banach spaces for which the group has the bounded orbit property, we would better look at a set, sort of a maximal set, for which the group has a fixed point property, but also closed with respect to taking subspaces and ultra limits, for reasons due to this topology. If we want that set not to be too topologically wild, this is one of the things these are two of the things that we should require. And then another thing that it's best to require is that we're looking at such a set also closed with respect to L2 finite sums. Now, the reason for that, and actually, not L2 sums, in fact, not just L2 finite. And the reason for that is that sometimes the fixed point property comes for unnatural reasons. It just comes from the fact that certain Banach spaces have very small groups of isometries. But then if we're allowed to take this space as well, this one has a geometry very similar to the other space, but it has a much larger group of isometries. So if we know that for such a space as well, the group has a fixed point property, that is a consistent condition. So, that would be a sort of relatively good definition of spectrum. And this is what we did with Ashot Minasyan and Mikael de la Salle. For a countable group, we defined a new spectrum for measuring the fixed point properties, which is in a sense really what we wanted. The largest set of uniformly convex, we had to restrict to uniformly convex Banach spaces for which G has the fixed point property. The largest set which is moreover stable by the operation of taking subspaces, ultra limits, and L2 finite sums. So in a way, this is sort of the best that you can get. The most accurate measure of the strength of the property T for that group. And what can be said about this set, first of all, is that it is open. It's the same philosophy, so we sort of deduce it from existing results. It's simply because the fixed point property is an open set, is an open property. So it is open in the topology that I mentioned before, introduced by Mikael de la Salle. The weak Shalom conjecture for this can be reformulating in the terminology of this spectrum as the property that this spectrum has compact closure for every hyperbolic group. And the results, previous results of de Laat and de la Salle can be used to show that if we take all the spectra for all the hyperbolic groups, this is going to cover the set of all the uniformly curved Banach spaces. Now, this is a definition that is introduced by Gilles Pizier, uniformly curved Banach spaces. A priori, it only implies uniformly convex, but it also covers all the existing constructions of uniformly convex Banach spaces. So it is an open question whether there exist Banach spaces that are uniformly convex and not uniformly curved. So this is to say that probably if there are, they must be very, like unnatural, so pathological examples. So in any case, if you look at the spectra of all the hyperbolic spaces, this is covering all this sort of large set of uniformly curved Banach spaces. So this follows from their work on random groups, in fact. And what we also proved is that if we look at the class of finitely presented groups, any spectrum that has compact closure must also be the spectrum of a hyperbolic group. So among the spectra that are relatively compact, everything is covered by hyperbolic groups. Any other finitely presented group must have one of those spectra. So let's say this is sort of the most accurate way of measuring the fixed point property, and this is what can be said up to now. Now, if we look at the other end, the proper actions, and in particular the Shalom conjecture, there are a few things that can be said. So first of all, there is a version of the weak Shalom conjecture for acylindrically hyperbolic groups. So we proved this with John Mackay. And so we proved that every acylindrically hyperbolic group does have an action, affine with uniformly bounded linear part on L1, or on, either small L1 or large L1. Now, this class of acylindrically hyperbolic groups is larger than the class of Gromov hyperbolic groups. Its definition is that we're just asking that the group has an action on a Gromov hyperbolic space that is acylindrical and non-elementary. It covers the hyperbolic groups, the non-elementary hyperbolic groups, but it also includes many other groups, like the mapping class groups, that are not virtually abelian, the groups of auto-orthomorphisms of free non-abelian groups. So it's a much larger class. And for all those groups, one can say that they do have an action with unbounded orbits, but on L1. So we can't extend this to Hilbert, because unlike the isometric uniform, the isometric affine actions, we can't move between L1 and L2, but we can say it for L1. And in fact, this result in this generality is optimal. So we cannot improve it in any way. So there would be two improvements that we would hope. The first one would be, well, instead of L1, let's say put Hilbert or LP. And the other one, well, instead of asking for unbounded orbits, so instead of the weak Shalom conjecture, we could try and aim to the strong Shalom conjecture and ask for an action that is proper. But neither of these two can be achieved. L1 cannot be replaced with any LP, so in particular it can't be replaced by Hilbert. And the reason for that is that there exists a cylindrical hyperbolic group that is a monster. So it is a combination of the work of Minasyan and Osin and de Laat and de la Salle. So Minasyan and Osin proved that there exists an infinite acylindrically hyperbolic group that is the quotient of every hyperbolic group. In particular, it will inherit all the fixed point properties of all the hyperbolic groups. Now, by the result of the Lat and the La Salle, if you pick any uniformly curved Banach space, there will be a hyperbolic group that will have a fixed point property for that space, which means that this acylindrically hyperbolic group will have the fixed point property for any uniformly curved Banach space and every affine uniformly Lipschitz action on it. So that means that we really cannot replace L1 by anything else, by an LP and by anything else, because of this example. If we want the statement to cover all the acylindrically hyperbolic groups, and we cannot replace the weaker conjecture by the stronger conjecture, we can't ask for proper orbits, and the reason for that is that there exists a particular construction of a Gromov monster. So the Gromov monsters are a set of infinite groups with the property that given a particular kind of expanders, so given infinite families of expanders that satisfy a particular property, we can embed them uniformly in the Cayley graph of that group. So this is a construction that Gromov devised in order to produce a counterexample to one of the Baum-Kohn conjectures. Not all of the Gromov groups do the job for what I'm about to mention, but there is a particular construction, so a modification of that construction due to Osaida, because that group, so first of all, that group contains isometrically embedded copies of an entire family of expanders, but more importantly, it is acylindrically hyperbolic, because Gromov monsters, so the main construction of Gromov monsters is also probabilistic, and the generic Gromov monster, in fact, is not acylindrically hyperbolic. This is a result of a tesseract systo, and there is a third co-author, and I'm sorry to say that I forgot him. But anyway, so we do need this construction of Osaida, but once we have it, we will have an acylindrically hyperbolic group that contains infinitely many expanders. And for that reason, it can't be uniformly embedded into an L1 space, because a family of expanders can't be embedded uniformly. Yes?
So these groups are finite generic, but not finite.
Yes, they're not. Yes. Yeah, I mean, all the yeah. So, and this one obviously is not either. Right. Well, I mean, for acylindrical hyperbolic groups, we're dropping that assumption, right? Because we have a lot of examples that are not finitely presented. There is, you mean, an example of group that has the fixed point property for all the LP spaces, lattices, of course, but they're not acylindrically hyperbolic. And of course, neither, they can't contain, they can't contain isometric copies of expanders either. So they're both constructions, in fact, again, come from this small cancellation construction, which is highly unnatural, but it's a very effective device for producing counterexample, annoying counterexample for you and crushing people's dreams and aspirations in more than one way. But, it's always good because then you have to think some more. Right. Now, for the actual Shalom conjecture, which is aiming at a proper action, so what we could prove with John Mackay is only restricted to residually finite hyperbolic groups. So if the group is hyperbolic but also residually finite, then we manage to prove that they do have an affine uniformly Lipschitz action on an L1. Moreover, it has undistorted orbits. So that means that the induced metric and the initial word metric are by Lipschitz equivalent. And of course, it can be done for either L1 or large L1. So if we let G act by uniformly Lipschitz affine actions, then we can produce a copy of G inside L1, and even a very accurate copy metrically. Right, sorry, but I'm actually at the last bit. Right, and so interestingly, actually, we were able to generalize this to Lie groups. So if we consider the Lie groups of isometries of one of the rank 1 symmetric spaces, then it's the same thing. We can produce an action on L1 by affine uniformly Lipschitz transformations, and again with undistorted orbits and continuous. So that means that again we can produce a copy of that Lie group inside L1 that is metrically very accurate. Now for this group, this is no news. In fact, there are better ways of doing that. But even for this group, it is. So of course it's known that this group is a-T-menable. So there is a proper action even by isometries on a Hilbert space, but the metric does not, I mean, it metrically does not behave well. It's definitely not, does not produce undistorted orbits. The lower bound for the distance is the square root of the distance, for the induced distance is the square root of the distance. And obviously for these two, it is news because these have property T. So it is like really version of the Shalom conjecture. And the last case that we could tackle is the case of the mapping class group of a surface. So we could produce in this case as well an action that is affine uniformly Lipschitz, again on L1. And here we were not able to show that the orbits are undistorted. The only thing that we could show was that we can produce a lower bound between the induced metric and the initial metric, and this row is not quite linear, so what we could find was only this. So the lower bound is almost linear in the distance, but not quite. There is a log. In fact, this means log iterated as many times as you want, but it's still there, unfortunately. We could not remove it. So partial results of this and the previous were obtained by Vergara. And in case you're interested, we can find a Lipschitz constant in each case. So in this case and the previous one, that is almost 2, in fact. So the Lipschitz constant is not wild. It's really pretty much 2. And I should also say it is in fact a consequence of the same property that I mentioned before, which is that the fixed point property is open for any group. So it's in a way a version of the Fisher-Margulis thing. We can go with the fixed point property a little bit beyond the classical setting. If a group has the property T, then it also has the fixed point property with affine uniformly Lipschitz actions if the Lipschitz constant is not very far from 1. And here this epsilon again depends on G. So that means that in any case, we'll have to go above 1 if we want, I mean, in this sort of Shalom conjecture. And what we get is, in fact, 2 plus epsilon. And I will stop here.
Thank you. Questions?
Very, very impressive talk. I was wondering, like, do you know, like, if there is any progress on understanding similar thing for quantum groups? Since you mentioned Lie groups, probably like.
Not that I'm aware of.
I had a question. Do you know, there's some spectrum of Banach spaces, SG. Is there any groups for which you know this explicitly, or are they just like too many Banach spaces, so it's some abstract thing you can never know?
We know a number of things, but no, we don't know it explicitly. Yeah.
Is there like a conjectural picture that, like, for some groups it should be only?
Well,
yeah.
there is, but I don't dare share it.
Oh, I see. Okay.
Might be false.
So you mentioned this uniform Lipschitz, but there's also this slow growth Lipschitz for the strong property T.
Yes.
Are there any groups besides higher rank lattices that are known to have this?
Yeah. So this is the, you're referring at Vincent Laforgue's result.
Yes.
Right? it's, I mean, in the strongest version, like really strong, the one in which he's actually, he has the property, essentially he's considering all the uniformly convex Banach spaces, and he's allowing for representations not just uniformly bounded, but just bounded in this way.
Yeah, with the slow north
Exactly.
in the word norm.
I think it's still the only class that is known is still the one of l'ensemble Laforgue, so SL3QP and lattices, if it's just that one.
And de La Salle does the non-uniform
exactly.
lattices.
If it's Hilbert, if just Hilbert but that growth, then de La Salle and Dalat proved it for lattices. For all the lattices, I think, right? I mean, Oppenheim proved it for SL and Z, and at least 4, and then they generalized it, and that's all I know. I mean, I don't think.
Okay, if there's no other questions, let's thank Cornelia again. Thank you.